Good morning. Today we're going to start off working through lesson number 2, and lesson number 2 has to do with number systems. We use the decimal number system. Decimal obviously because it is in base 10. If we look at what the characteristics of a number system are, point number 1, we need some symbols to represent digits. Because we are in a decimal number system, we need 10 of them. So that is the first characteristic of a number system, is it needs a set of unique symbols equal to whatever base you are in. So we are in base 10, which means we need 10 symbols, and these are them over here. These are the ones that we use. Obviously, if you're in China, you would have different symbols, or if you're in Arab country, you would have different symbols because of Arabic. So different languages have different symbols, but they will have 10 of them. And each one of them has a different value. So this one is worth more than that one. And this one is worth more than that one. This one is worth more than that one, etc., etc. What is the second characteristic of any number system? Is that when you write a number, the adjacent digits, the digits that are next to each other, have different value. We call it ordinal value. So each adjacent digit is, we call it an order of magnitude different. So that is the characteristic of a number system. So let's just take, for example, this is just some random number that I just thought up, the number 5,784. So this number here, 5,784. So let's have a look at that. We break it down into its pieces. This is something you did in junior school, so this should not be new. You see here we have the ones column, here we have the tens column, here we have the hundreds column, here we have the thousands column, and obviously this would go on and on and on and on. If this number was bigger, we would have the 10,000s column, the 100,000s column, and the millions column, etc., etc. And we can see that each column, like we said up here about having orders of magnitude difference, we see that each column is 10 times bigger than the one next to it, obviously because it's the decimal system. So why have we got 1 and 10 and 100 and 1,000? Well, in fact, that first column is 10 to the power naught. That's the base we are using, 10. 10 to the power naught. Now in arithmetic, anything to the power naught, it doesn't matter what number it is, any number to the power naught is equal to 1. So 100 million to the power naught is 1. That's just a definition in mathematics. So next to that we get 10 to the power 1. 10 to the power of 1 is 10. Then we got 10 to the power of 2. 10 to the power of 2 is 10 times 10, which is 100. Then we've got 10 to the power 3. 10 times 10 times 10 is 1,000. And if we had another column, it would be 10 to the power of 4, and 10 to the power of 5, 10 to the power of 6, 10 to the power of 7, 10 to the power of 8, and so on and so on. So let's have a look and see this number that we've got here, 5784, 5,784, means that we have got 5 thousands. So you've got 5 by 1,000, plus we've got 7 100s, plus we've got 8 tens, 8 times 10, plus, and we've got 4 ones. So that there is what my number is. I've got 5 thousands, 7 hundreds, 8 tens, 4 ones. And if that's all added up, it comes to 5784. So this is not something new. You will remember this from junior school. Okay, so that is decimal number system. So why have I shown you that? Well, let's go and have a look at the binary number system. So the binary number system is a number system just like the decimals, but a big difference. It uses base 2, not base 10. Okay, so we're in base 2. So we know that our number system, going to have 2 symbols. There they are. We just use 0 and 1. So we need 2 symbols for a binary number system. So the same way of thinking, okay, I've just once again come up with a random binary number, and here it is, 110011. So we've got that random binary number, 110011. So thinking about this, just like we did with the decimal system, let's break this number up into its columns. So we start off with the ones, just like we did in the decimal system. We've got the ones column. Then in decimal, each column was 10 times bigger. But this is the binary system. So each column in this case is going to be 2 times bigger, not 10. So we've got 2. 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. 16 times 2 is 32. And that would carry on. It would be 64, 128, 256, 512. If we carried on, each column would be getting bigger by a factor of 2. And just like we had with the decimal, that is 2 to the power 0. Always start with 0 in the first column. So 2 to the power 0 is 1. 2 to the power 1 is 2. 2 to the power 2, which is 2 times 2, is 4. 2 to the power 3, which is 2 times 2 times 2, is 8. 2 to the power 4, which is 2 times 2 times 2 times 2, is 16. 2 to the power 5 is 32, etc., etc. And that would obviously carry on to infinity, depending on how big your number was. So let's break this number down, just like we did with the decimal. So we can see that we have got 132, there it is there, 132, plus we've got 116, there it is there, 1 times 16, plus we have got no 8s, there you can see it, 0 times 8, plus we have got no 4s, 0 times 4, plus we have got 1 times 2, plus, and we have got 1, 1. So I've got 132, 116, no 8s, no 4s, 1, 2, and 1, 6. I've just read those out of the columns here. And if I add that up, I get 32 plus 16 plus 2 plus 1 gives me 51. So there I've just shown you how to convert a binary number into a decimal number. Binary 110011 is equal to 51 in decimals. Okay, so that is the second number system that we've just learned about. And obviously binary number systems we have to know because computers use binary number systems. Okay, so the third number system that we need to know is the hexadecimal system. Hexadecimal, hex for 6, decimal 10, so it is base 16. Okay, so hexadecimal number system, base 16. The same rules apply. This is a number system, just like any other. So the same rules apply. We know that because it's base 16, we need 16 symbols to be able to use it. We need 16 symbols. So for convenience, we are going to use from 0 to 9, which is what we use for decimal, but that's not enough. We need more. we need another 6. So we're going to use A, B, C, D, E, and F. So A is going to be a 10, B is 11, C is 12, D is 13, E is 14, F is 15. Okay, so we've got from 0 to 15, or 0 to F. Those are the symbols that we are going to use. So let's take another example. So here's a hexadecimal number, 3E7A. So that is a hexadecimal number. It's a number made up of the hexadecimal digits, 3E7A. We break it up into its columns. Here we go. We've got the ones column, just like we did with decimal and binary. We start off with the ones column. Now in decimals, we saw that each column got 10 times bigger. In binary, base 2, we saw that each column got 2 times bigger. Here, we're in base 16, so each column is going to get 16 times bigger. So we've got 1, 16, which is 16 to the power of 1. Then we got 16 to the power of 2, which is 16 times 16, gives us 256. Then we got 16 to the power of 3, which is 16 times 16 times 16, which is 4096. And next to that, we'd have 16 to the power 4, 16 to the power 5, 16 to the power 6, and so on up until infinity, depending on how big the number is that you've got. So let's see what that number represents. We have got this number, 3E7A. So that means I've got 3 4096s. There they are, 3 times 4096, plus I've got E 256s. There's my E times 256, plus I've got 7 16s. There it is there, 7 times 16, plus, and I've got A1s. A1s, A times 1. So that is what my number is. Let's start working that out. So I've got 3 4096s. I take my E and I replace it with 15 because I know that E is 15 from up here. Sorry, that is incorrect. Okay, that is incorrect. E is 14. Okay, so the answer here is going to be wrong. This here is 14. E is 14. It's F that is 15. Okay, so I'm sorry about that. That is just an error here in my example. You must just make sure that you use a 14 here. So that is 14 times 256. We have got 7 16s there. So there's 7 times 16 plus 10 ones. A is a 10. Okay, A is 10, 10 ones. I then add that up and I get that, which we know is wrong because that should be a 14 instead. But the principle, that's how you do it. That's the principle is how you do it. Okay, so that there is how you would convert a hexadecimal number into a decimal number. So to convert any base, okay, I've shown you how to do binary and I've shown you how to do hexadecimal. But if you were, say, an octopus and you were counting in base 8 because you've got 8 beautiful tentacles, then if you had an octal number, okay, base 8, they call that octal, and the digits would be from 0 to 7 because you need 8 of them. So 0 to 7 gives you 8 digits. And if you were converting an octal number, then obviously your columns here would be 1, and then there would be an 8, and then it would be a 64 because that would be 8 times 8, and then next to that would be 8 times 8 times 8. So your columns would be in orders of 8, not 16 or 10 or 2 like we have done before. So you can convert any base, it doesn't matter what it is, any base, you can convert it into decimal using this method. You just break it up into its columns and then you add them up. Okay, that's how you convert any base into decimal. So the last thing I want to show you is how do we actually write these numbers? Okay, so decimal numbers, there's a number, 3578, and you can see I've written a little 10. Okay, they call it a subscript, little 10 after that. So by rights, we should do that with every single number that we write because we use the decimal number system. But because 99.99999% of all the numbers that we use every day are always decimal, we just leave it out. So if you ever see a number with no subscript, then you know it's decimal, okay, because that's how we do it. Here's a binary number, 100111011. To indicate that it's a binary number, I put a little subscript 2. Okay, you put the base, whatever number you're in, the base, you write it as a tiny small number at the end. So you can see I've put a little 2 there. That shows that's a binary number. Hexadecimal numbers, there are actually 3 ways to indicate that if we've got a hexadecimal number, and all 3 of them are correct. So I don't mind which one you use. All 3 are correct. The first one, like we saw up here, is just to put a little subscript 16. So there's my number, B34E, and I've put a tiny little subscript 16 at the end to indicate that I'm in base 16. Another thing that I can do is I can take my number, B34E, and I can put 0x. Okay, so it's a number 0 and a small x. I put 0x in front of it. Now the 0x is not part of the number. That is very important. Okay, I've seen people get confused with this. They think that that is 0 times B34E, or they think that the 0 is part of the number, but it's not. The 0x is just to indicate that what comes after that is a hexadecimal number. So that is super important. 0x, not part of the number. It's just telling you that the number is a hexadecimal number. The third way to do it is to actually put a little h, okay, at the end of it. So the number is B34E with a lowercase h at the end. Now this is important as well because the h is not part of the number. Okay, I've seen some people get confused thinking that f is 15, so h must be 17 or something like it, but that is not what it is. The h is just there to show you that the number B34E is hexadecimal. So the h is not part of the number. It just shows you that it is a hexadecimal number. Okay, so what you should do is just give this a go yourself. Just write down a couple of binary numbers and write down a couple of hexadecimal numbers and see if you can convert them into decimal using the system that we've just done, which is just break them up into their columns and then just add them up.